Today we're going to talk about NMR spectroscopy. Where we start is by looking at protons and neutrons, and that those particles have intrinsic spin of 1/2. Now nuclei, or combinations of protons and neutrons, might also have spin, and that forms the basis of NMR spectroscopy. Now, the spin operator for nuclei follows the general form in that I squared psi equals I plus 1 h bar squared psi. Now, one key difference between spins of electrons, which we often denote S, for nuclei we denote the spin as the letter I. Now, if we look at the projection operator on, say, the z-axis, all right, that also follows the general form of m sub I h bar squared psi. Okay, and what we want to look at for nuclei is the magnetic dipole moment of a nucleus. Now, this is the average electric current in the nucleus. Okay. Now, this is different than the electric dipole moment, which looks at the distribution of charge around, some arbitrary object, for example, the nucleus. Okay, so we're looking at the average current in the nucleus. Now, let's take for an example some charged particle, okay, that orbits around in circular motion, okay, about some center of radius r, and this particle has some linear velocity v. Okay, now we define the magnetic dipole moment as mu, and mu equals the current of that particle times the enclosed area. Okay, so I is current, A is enclosed area. All right, cool. So let's look at our circular motion again. Now that area, the enclosed area, is pretty obvious. It's a circle, right? So pi r squared. Okay. Now for the current, however, what we have is we have this. We want to look at coulombs per second, right? And so what does that mean? Well, that's going to be, okay, so the current I is coulombs per second. So that's going to be the charge times the angular velocity, which is the charge times the linear velocity over 2 pi r. And that is going to be our current I. Okay, cool. So if we recall, mu equals the area times the current, okay, and we said the area was pi r squared, okay, and our current was the charge times the linear speed divided by 2 pi r. All right, so then mu becomes the charge times r times v over 2. Neat. And again, these formally, if we're looking at it classically, are vectors, and formally that is going to be a cross product. All right, is q, and then it's r cross v, okay, over 2. All right. So, formally speaking, we're looking at that cross product between the linear velocity and the radius. Now, what we can note is that angular momentum L is the cross product of r and p, the momentum, and momentum is m times v. Okay, so making that substitution, what we find is that mu equals the charge divided by 2. All right, and then we substitute in momentum for velocity. Okay, so we have an m here, and we have r cross p, which gives us the angular momentum. Cool. Well, we're talking a quantum mechanical picture, not a classical picture, so we need to go to the angular momentum operator, and then if we look at that in one dimension, okay, the eigenvalues for that are going to be m sub L or m sub I. But in this case, we're just looking at some arbitrary charged particle, so we're going to leave it in terms of L for the quantum numbers. So in that case, it becomes, the dipole moment becomes Q times m sub L h bar over 2m. Okay? Alright. So again, those eigenvalues are h bar times m sub L. Alright, cool. So we've found out what our dipole moment is. Alright, so now let's look at specific particles. So if we look at the particle in terms of electron, right, fine, we have the charge then is going to be elementary charge. We have h bar squared. We then have m sub L, which is going to be plus 1/2 or minus 1/2 for an electron, and 2, and then the mass of the particle in this case is an electron. Neat. Well, what we can do is we can combine all the constants outside of m sub L. Okay, those are all just constants. We combine them into something called mu b, which is called the Bohr magneton. Okay, in a similar way, instead of looking at an electron, if we look at a proton, okay, we have m sub L times E h bar squared over 2 times the mass of the proton. And that quantity, that conglomeration of constants, that's called the nuclear magneton. Okay, neat. Well, alright, fine, but that's a perfect picture, right, of a charged particle going in a circular orbit. And our picture of a proton in a nucleus, or a nucleus itself, is not this perfect picture. It's not this single particle in a circular orbit. So we want to introduce a fudge factor, and that fudge factor we call the G factor. Okay? Now, how we introduce that is we just put it into our relation. So then we just say mu equals this G factor, okay, times m sub L times mu n. Okay, so we just introduce a multiplicative fudge factor. Okay, now for a proton, if it were ideal, we'd expect this G factor for angular momentum to be 1. Okay, because for that perfect particle, it has the charge of E, right? So it's a charged particle in a circular orbit. So that's ideally. Okay, now for an uncharged neutron, we expect the G factor to be 0 because that neutron is not charged. So as it orbits around in a circle, it would not impart, no current would be generated. Okay, fine. So that's ideally. Now, so far we've only discussed orbital angular momentum. Okay, we haven't discussed the intrinsic spin of these particles. All right. We can, however, draw an analogous expression for mu if we're only looking at the spin rather than the orbital angular momentum. In that case, we get some dipole moment from the spin, which has a spin G factor, m sub s, which is the projection of spin, and again this nuclear magneton. Now, it turns out that for protons and neutrons, this G factor is different. Okay, so for protons, it's about 5.58. For neutrons, it's minus 3.83. And this is weird, right? Why would we expect these G factors to be such odd numbers? Well, these are empirically determined, they're measured, and it's complicated to determine these from first principles because protons and neutrons are made up of elementary particles themselves, quarks, and so these G factors are a function of all of that mess, and it's beyond the scope of what we're talking about, where those spin G factors come from, but they do in fact exist. Okay, cool, fine. So we know what those G factors are. And in the end, the total magnetic dipole moment is the sum of the orbital term and the spin term. Now, the protons and neutrons fill orbitals just like electrons do, and can achieve orbital angular momentum. Now, a hydrogen atom is in an s orbital. The proton in that hydrogen nucleus is in an s orbital and has no orbital angular momentum. Therefore, if you look at the G factor for a hydrogen nucleus, it's just the G factor for a bare proton, which is kind of neat. All right, cool. Well, let's introduce one more interesting quantity, and that's the so-called gyromagnetic ratio, gamma. All right. And all that gamma does is it really includes both the G factor and the nuclear magneton and kind of groups them together. And also, it incorporates an H bar for reasons that we'll kind of see later. So in that case, if we make that substitution, we can write our magnetic moment as H bar gamma times m sub I or m sub L. Okay, so now we're switching over to talking about I, where that's the projection of nuclear spin. Okay, neat. Now, where does NMR spectroscopy come in? Well, if we're in the absence of an external magnetic field, all of the M sub I states have the same energies. We would not expect them to be any different. Okay. However, if we're in an external magnetic field, the energies of those orbitals is minus mu times B naught. Okay, where B naught is our magnetic field. Okay, and we have an analogous expression for the Hamiltonian. Okay, it's this mu operator times B naught. Okay, now often we care only along the axis of that magnetic field, which we often call the z-axis. Okay, so in that case, we want to look at that Hamiltonian is just in that z dimension. Okay, or if we want to look at it in terms of this gyromagnetic ratio, it's minus gamma times I sub z B naught. Okay, where we just have that projection operator. Okay, fine. Now that leads to energies, okay, that are minus G times mu n times M sub I times B naught. Or if we have that, if we use the gyromagnetic ratio instead, minus H bar gamma mu n M sub I B naught. Okay, so the only difference there is that we're using the G factor in the nuclear magneton or the gyromagnetic ratio. And you can notice there's an H bar difference between those just based on the definitions of those things. Okay, fine. So what does this look like for a proton? Okay, so if we have a proton with no external magnetic field, no B naught, right, those two M sub I levels, okay, minus 1/2 spin down, or M sub I plus 1/2 spin up, are the same energy, right? So this is energy axis going up. However, when we add a magnetic field, they split, okay? And those energies are different. And so we have a spin up or alpha state, a spin down or beta state that have different projections and now different energies. So let's quantify that. Okay, fine. So we want to look at delta E, or the change in energy between that beta state and the alpha state. Okay, well, we just plug in from the energy formula above, and for that minus 1/2 state, we get 1/2, okay, which is the projection. So it's minus M sub I, so a minus 1/2 is a positive 1/2. Okay, the G factor, G, okay, times mu n B naught, okay, minus a minus 1/2 G I mu n B naught. All right, so what that comes out to be is Gi mu n B naught. Huh, that's neat. Okay, which also, which is that energy difference. Cool, well, we have an energy difference between two states, so we can also consider that energy difference and the radiation that would be necessary to excite those transitions, h nu. Cool, well, we can set those delta E's equal to each other. Right, so here we're going to set that h nu equal to Gi mu n B naught. Cool. Well, let's solve for the frequency needed to do that. Fine, so we just divide by h. Now we can kind of substitute in from the G factor in the magneton, nuclear magneton, to this gyromagnetic ratio and h bar. Okay, well, h bar is just h over 2 pi, so the h is canceled and we're still left with the 1 on 2 pi. All right, and so we have this frequency, which is mu times b over 2 pi. And this frequency is called the Larmor frequency. That's the frequency needed to do this spin flip from spin up to spin down in the nucleus. Well, that's pretty neat. Cool. Well, in order to observe this change, there has to be a difference in population between the upper state and the lower state. If there's equal amounts of population in both the spin up and spin down state, you're not going to measure any absorption of frequency, because the probability of going up and absorbing energy, or from going up to going down, is going to be equal. So we need this difference. Okay, so we can calculate this fine. So if we find the ratio of the two, well, that's Boltzmann, right? All right, so that ratio from Boltzmann is equal to E to the minus delta E over KT, right? I'll recall that. All right, well, we know delta E. We had found that before. It's minus gamma H bar B naught. Now, we're not going to go through it here. It's in your book if you want to look at it, but just some algebra and approximation to get then from this ratio to the difference. The difference between alpha and beta states, the n, where n is the number of them, is gamma H bar B naught over 2kT times the total number of molecules that you have. All right, so for example, if you plug this in at 20 degrees Celsius and a sample size of 100,000, and look at this, the difference in population between spin up and spin down is 3.5. It's crazy. So out of 100,000 molecules, you have roughly 50,000 molecules in spin up, 50,000 molecules in spin down, and a difference of 3.5. That's tiny, tiny. But NMR spectroscopy is very sensitive and is able to see that small difference. Now, one way that you can make this population difference bigger is by reducing the temperature, right? Because these are thermally populated, and that energy difference is so small that both of them are appreciably populated thermally. So if you decrease the temperature, you're going to decrease the population in that upper, quote-unquote, excited state of spin down. So that's one way you can increase this. Now, let's look at this frequency, this Larmor frequency for protons in an external magnetic field of 10 Tesla. Fine, so we can look at this frequency. It's mu n times b naught over 2 pi, all right? Now we can look at the gyromagnetic ratio, gamma n, the gyromagnetic ratio. We can look that up for a proton. It's 2.675 times 10 to the 8th per Tesla per second, all right, times the external magnetic field of 10 Tesla divided by 2 pi. Now that comes out to be 425 times 10 to the 6 hertz, which is 425 megahertz. So our NMR instrument is a 400 megahertz instrument, and what that specifies is roughly, not exactly 400 megahertz, but right around 400 megahertz to excite a proton, which means that our magnetic field is about 10 Tesla. Not quite, it's a little under 10 Tesla for us. But that's why NMR instruments are characterized by a frequency. That's the Larmor frequency, and typically quoted as the frequency needed to excite a proton in the magnetic field of that instrument. And as you increase the increase that Larmor frequency, that corresponds to a direct increase in the magnetic field. And as you increase the magnetic field, you increase the splitting between the two levels, which is another way to increase that population difference. If that delta E, the splitting difference, gets bigger and bigger, you're going to have a larger difference in population. And we'll talk later about how this also has a direct effect on the resolution of the spectra that you can obtain. But for now, that's it.